All right, assigning quantum numbers. So, just like in Battleship, you guys had a energy level, you had a sub-level. What are you doing?
Taking a picture of it.
You know you can just get on OneNote. So, just like Battleship, you guys have an energy level, you guys have a sub-level, and then you guys have a certain number that indicates where the last electron is filled in based on the location of your element on the periodic table. Here, we're going to quantify it. What does it mean to quantify something? Quantify? Quantity. Number-based. We are going to apply numbers to what you guys already know how to do systematically with electron configuration. So basically, we are going to assign what we call quantum numbers for every detail of the last electron filled in to an atom. So, you have 4 quantum numbers. The principal quantum number is your energy level. The orbital quantum number is your sublevel. The magnetic quantum number is the specific orbital that the electron is filled into in your sublevel. And then you have your spin quantum number, which shows you the spin of the electron in that orbital. So basically picture this as the mailing address of your last electron filled in. Now, how many energy levels do you have? 7. So your energy level, principal quantum number N, can equal 1 through 7. Now, how many sublevels do you have? S, P, D, and F. You have 4. So, you have 4 sublevels. We are going to assign S as 0, P as 1, D as 2, F as 3. So you can have a total of 4 different orbital quantum numbers, which have L as your variable. All right. Now take a look at the magnetic quantum numbers. You can have up to -3, a range of -3 to +3, but it all depends on what sublevel we're talking about. So, if we're looking at the individual orbitals in the sublevel, each S sublevel has how many different orbitals? How many lines does it have? 1. So, we always start with the center, and we label that 0. P, how many sublevels do you have?
3.
Or sorry, how many orbitals do you have? 3. Start in the center, 0. Then it's like a number line. +1 to the right, -1 to the left. D, how many orbitals do you have?
5.
Start with 0 in the center, +1, +2, -1, -2. F, how many orbitals do you have in the F sublevel? Start with 0 in the center, +1, +2, +3, -1, -2, -3. So based on that last electron filled in, we are going to determine which orbital it fills into with that notation. So, F has all of these values, while S only has one of those values. And last, is your electron spin up? Or is your electron spin down? +1/2 if it's spin up, -1/2 if it's spin down. So, what does all this mean? Well, let's take a look at some examples. Give me an element in the 2p. Any element in the 2p? Boron? Boron ends on what? Battleship. 2p1. So if I go to my 2p's, I'm going to put 2p1, my last electron filled in, is this spin up electron in the 2p sublevel. What energy level am I in? 2. What sublevel do I have? P, which is equal to 1. So 2, comma 1, comma. Which orbital am I in? -1. And am I spin up or spin down? Spin up. So positive 1/2. Give me an electron in the 5s. Rubidium. Which ends on what? If you're not looking at the periodic table right now, you are not participating. 5s1. So rubidium is 5s1. So I go to the 5s, I fill in my 1 electron, spin up. My energy level is what? 5. My sublevel is S, so what numeric value do I assign? 0. My orbital is what? 0. And my spin is plus 1/2. Give me something in the 3D. How about zinc? Zinc? 3D? 3D10?
Sure.
So, zinc is 3D10. So I go to 3D. Spin up, spin up, spin up, spin up, spin up. Down, 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 down. What was the last electron I filled in? Right there. Down in the +2. So, my energy level? 3. My sublevel? D is 2. My orbital? +2. And my spin is -1/2. So you're just finding the last electron you are filling in, and then you are assigning 4 quantum numbers each time. Think we can do it? Let's give it a try. Here's 3. Assign quantum numbers for lithium, sulfur, and molybdenum. Ready, set, go. Okay, so lithium, what does it end on? 2s1. Sulfur, what does it end on? Sulfur, what does it end on? 3p4. And molybdenum, what does it end on? 44. So 5s2, 4d4. Remember, molybdenum is an exception just like chromium. So really, we borrow 1 electron from the 5s. So it's 5s1. And the last electron filled in is actually going to be 4d5. So, let's take a look at lithium first. 2s1. 2s, spin up. So here we are filling in that last electron in the 2s, spin up. So, for lithium, energy level, 2. S sublevel is 0. It's a 0 for the orbital. And spin up, so plus 1/2. For sulfur, 3p4. 3p, 1, 2, 3, 4. So that is your last electron filled in. 0, -1, +1. So energy level, 3. Sublevel, 1 for P. Orbital, -1. Spin, -1/2. Molybdenum ends on 4d5. So 4d, spin up. Oop, wrong color. Spin up, spin up, spin up, spin up, spin up. There's 4d5. What's my energy level? 4. What's my sublevel? 2 for D. What's my orbital? 0, plus 1, plus 2, negative 1, negative 2. I am plus 2. And what's my spin? Plus 1 half. Questions? So, good question. How does this apply outside this classroom, or why even assign quantum numbers in the first place? When we talk about statistics, how do you quantify or apply statistics to an up arrow or a down arrow or even a letter, S, P, D, F? So a lot of times when we are applying stats or really just trying to quantify anything, we have to apply numbers to it so that we can actually mathematically do calculations to derive whatever it is that we're trying to derive. When we talk about electron configuration in general, this is almost a stepping stone to understanding some of the stuff that we've actually already covered, but definitely some items that we'll cover in the future. So this question is actually a great segue into where we are going next. If we jump over to... Actually, did we already cover the exceptions? Copper? Do we do exceptions to the rule with copper? And we just did molybdenum? Did we cover these graphs?
No.
Well, real quick, again, this is a good question, but like when we look at some of the trends that we collect data on in chemistry, one, first ionization energy. Why do we look at electron configuration? Well, this is actually the entry point to explaining why certain trends happen. So if you look, once again, at period 2 in the first ionization energy, this isn't a linear trend. You have these exceptions where instead of increasing as the ENC increases, hey, why do we drop off here and it's easier to pull the first electron off of boron versus beryllium, or off of oxygen versus nitrogen? So again, we see that half-hole rule that we talked about yesterday, that we can now quantify with our values that we did today, that half-hole rule explains why this is more of a zigzag trend than a linear trend. It explains why we have exceptions. Later on, we'll use this same information to talk about why or how bonding works, how some bonds are stronger than others, how polarity works. So there's a lot that is based on the foundation that you guys are studying right now. A lot of times I refer to chemistry as curriculum that always snowballs on itself. We just keep growing. So if you don't understand some of the foundational work, it's hard to really understand some of the future work you guys will do with chemistry.
Exactly.